Hello and welcome again to Flipped Harbor for Calculus. In this video we're going to be taking a look at the power rule for derivatives. Our objectives for this lesson are to learn how to apply the basic differentiation rules that include the constant rule, the sum and difference rules, the constant multiple rule. I'm going to take a look at some things that you should not try because we do have special rules coming up called the product rule and the quotient rule. And I want to point out what you can't do right now. I know you're going to try to do this, but you can't. Then we're actually going to take a look at the power rule itself, which is our first real rule about how to take a derivative without using the limits. Then we're going to apply all of these rules to taking the derivative of a polynomial. And then we're going to take a look at some other uses of the power rule, specifically with how to use it to take the derivative of roots, how to take the derivatives of some products, and how to take a derivative of some simple quotients. So first of all, I actually want to talk about some different notation that you're going to see for taking the derivative. The top row we see f primed of x, f double primed of x, and we've seen that before. And that's read, the derivative of f, the second derivative of f, the third derivative, so on. So we're going to see that notation a lot because that's probably the prime notation that we use in calculus when we want to signify that we're taking the derivative. In the second row, when we see these little fractions in front, this means to take the derivative, specifically stating that the variable, our independent variable in the function, is the x. So this first one is read the derivative with respect to x of f of x. The second one, when we see that square, it's not really a square. Yes, it looks like a square, but it's notation that means the second derivative with respect to x, and then the third derivative with respect to x, and so on. The bottom row, we're really not going to use a whole lot. I don't think I ever actually use it in calculus. It's actually used more in the field of physics, and it's referred to as dot notation. And I think the reason that we see it more often in physics, putting the dots above, it's a nice, neat way to do it when you're dealing with these big physics equations that we have to take the derivatives of. But I think even more really is to pay homage to Isaac Newton. That's the notation that he invented. Physicists, they just adore Newton, so they decided to use his notation rather than the top notation, which is actually from the German mathematician Leibniz. Alright, so first of all, our most basic differentiation rule that you need to know is that when we take the derivative of the independent variable, basically when we take the derivative of x, it's equal to 1. If we try to take the derivative of a constant, doesn't matter how big that constant is, doesn't matter whether it's a fraction, a decimal, a negative, when we take the derivative of a constant, it's equal to 0. Now remember, the derivative is just a fancy word for the slope. So if I asked you what is the slope of the line y equals 5, well, you'd probably be able to tell me, well, the slope is 0. It's a horizontal line. Well, that's a really good explanation about why the derivative of a constant is 0. Well, the slope of a constant is 0. Our sum and difference rule, real simple. It lets us break up our functions into smaller chunks and basically, take the smaller bites, chew them up, and deal with them one at a time. The sum or difference rule just simply says that if I want to take the derivative of a sum or a difference, what I can do is take the derivative of the individual pieces and then add or subtract them up, whatever it happens to be. So you see here a combination of the two notations. I've got that derivative with respect to x, and then over here on the left side, we see this prime notation, which is saying take the derivative of f, take the derivative of g. Okay, our constant multiple rule, this is a really important one because we deal with constant multiples all the time. So this is not when we have just a plain old constant, but when that constant is sitting in front of something that has a variable. Well, what we can do is just move that constant out in front and deal with the derivative that I have to do some work on. So if we take the derivative of 5 times something, then we can just move that 5 in front and take the derivative of the function with the x, ignoring that 5 for a little while. Now, this is I'm going to call it the not product rule. Okay, when you have a product, there is a specific rule that we're going to be learning later. This is not it. You have to fight this temptation because we've looked at the sum and difference rule and it's so basic, it's so simple. This does not work with the product. I can't take the derivative of a product by taking the derivatives separately and multiplying them together. This does not work. Don't write this down as a rule. I'm just saying we're not going to be able to do this. I'll show you how to deal with a simple product towards the end of this video, but this is not how we're going to deal with it. Similarly, this is the not quotient rule. Okay, so if we try to take the derivative of a quotient, that's where we have, maybe a polynomial on top and a polynomial on the bottom of a fraction, we do not simply take the derivative of the top and take the derivative of the bottom. Now, I just noticed a problem here that we're going to need to deal with later. This is from copying and pasting. This should say quotient right here. I'm going to let it roll for right now, and hopefully in a couple years I'll change this video. Alright, so here it is, the power rule. It's our first rule that's going to make finding the derivative really super duper easy. We're not going to need to take that limit as h goes to 0 anymore. You ready? Here it is. The power rule tells us that in order to take the derivative of an x squared, an x cubed, an x to the fourth, an x to the 22nd, doesn't matter what that power is, we move that power down in front. It becomes a product, and we reduce the power by 1. So just to throw up a simple example, if I want to take the derivative of x cubed, I'm going to bring that 3 down in front, and I'm going to reduce my power by 1. Now, this is really, really important. This subtracting 1, it's always minus 1, no matter what the power is. If we've got some oddball power up there, the power rule says subtract by 1. Always subtract 1, no matter what that oddball power is. Okay, so now let's apply all of these rules and take the derivative of a polynomial. So the first thing I'm going to do is realize, because of these sum and difference rules, I can deal with each of these chunks separately. I don't have to deal with the whole thing all at once. I'm just going to deal with each term in this polynomial separately, and I'll just preserve whatever sign is in here. So I'll take the derivative of the first term plus, take the derivative of the second term minus, take the derivative of the third term plus, and take the derivative of the fourth term. And I'm just going to apply all my rules that I need to apply. So in that first term, I've got a power. So I'm going to bring that 3 down in front. The new power becomes a 2. My constant multiple rule is going to be used by on the 4, so that 4 just sits there, and I use my power rule on the x squared. I'm going to simplify that in a little bit. My constant multiple rule works with the 3 times x. I take the 3 and I just let it sit there, multiply by the derivative of x, which we saw was 1, and then I've got a constant at the end, so I add the derivative of the constant, which is 0. So when I'm all done with this, I go ahead and multiply the 4 and the 2 together. The 3 times the 1 becomes a 3, and I just throw away that plus 0. So the derivative is equal to 3x squared plus 8x minus 3. And this is going to be something that you get so used to. If I ask you to find the derivative of this polynomial in a week, you're just going to rattle it off. You're not going to have to do that middle step at all. Okay, now let's take a look at some other uses for the power rule. What we're going to do is apply that power rule to roots. We're going to take a look at how to do the product of two polynomials. And we don't actually know the product rule yet, so we're going to have to deal with that in a special way. And we're going to take a look at some simple quotients. So when we want to take the derivative of some roots, what we need to do is change that root into a fractional power. So this should be something you're familiar with. How to change a root into a fractional power. You should know how to do from algebra 2 and all that. So I changed the square root here into a 1/2 power, and now I apply my power rule. So In order to apply this power rule to this, I'm going to bring the 1/2 down in front so we see the 1/2 as a multiple in front now. And I need to reduce the power by 1. I'm taking 1/2 minus 1 becomes my power. So 1/2 minus 1 is a negative 1/2. Now I'm not done. My general rule of thumb is whatever form they give me the problem in, that's what I'm going to try to turn the answer into. So I was originally given a square root. I wasn't given a fractional power. So I'm going to do stuff to simplify this fractional power and to turn it back into a root. So the first thing I do is I deal with the fact that that's a negative power. So that means that I push it to the bottom of the fraction and it becomes a positive 1/2 power. And then I know that a 1/2 power is a square root. So I change it back into a square root. Now, you know, a couple of years ago when you were in Algebra 2, they would have said, oh, you can't leave square roots in the bottom of a fraction. Listen, this is calculus now. We've got bigger fish to fry than rationalizing the denominator. So you can absolutely just leave your answer just like this. You're going to get every single point as long as you did the derivative right and as long as you do some simplifying. Okay, let's take a look at how to do a product. Now, we do not just take the derivative of these two polynomials separately and multiply them together. This is not what we do. We don't say the derivative of x squared plus 1 is 2x, the derivative of x minus 4 is 1, and multiply those together. Instead, what we're going to do is we're going to FOIL these two polynomials together, and then I'm going to take the derivative. So x squared plus 1 times x minus 4 becomes x cubed minus 4x squared plus x minus 4. Now there's no calculus there. That is all just algebra. Then I apply the calculus. I actually take the derivative, I use all my rules, and I get 3x squared minus 8x plus 1. So if you're asked to take the derivative of a product, what you've got to do right now is do the algebra to figure out what that product is and then take the derivative. Now let's take a look at how to use the power rule to take the derivative of a simple quotient like this. I have 1 over x squared. There is a quotient rule coming up that you're going to learn, not in this video, but right now what we need to do is think, how can I turn this into a power? And what I do is I turn it into a negative power. So this turns into the derivative of x to the negative 2. No calculus has happened yet. I still have not taken the derivative. I've just done some algebra to make it into something that I can apply my power rule to. So now I bring that new power, that negative 2, down in front, and I subtract 1. Now stop and think about this. Negative 2 minus 1 is a negative 3. My power became more negative. Now that's okay. I'm following the rule. I'm right. And the last thing I'm going to do is, again, my rule of thumb, give the answer in the form that they gave it to me. The original problem was given as a quotient with the variable on the bottom, positive power, so that's what I'm going to do. I'm going to push the x term down to the bottom of the fraction so that it's a positive power. I get negative 2 over x cubed. All right, how do we deal with a not so simple quotient? Now I've got this big polynomial on top. I've got just a little measly x. I can't get this too complicated and still be able to use the power rule. But one thing I can do is just distribute this x through to each term. So I'm going to take x cubed divided by the x, and that's how I get this x squared. 2x squared divided by x becomes 2x. And again, 1 divided by x, I turn it into a negative power. Take my derivative of each piece in this new thing. Derivative of x squared is 2x. The derivative of 2x is 2. And I bring that power down front, and it becomes minus x to the negative 2. Now I'm going to go ahead and do a little bit of simplifying. I'm going to change that little fraction at the very end, so I've got a positive power. And since they did give me one big fraction to start, if I multiply the 2x and I multiply the 2 by x squared, that lets me create a common denominator, and I can write it as one big fraction, just the way that it was given. Okay, so that's it. It's time for you to try some of this stuff on your own. I'll see you in class, and I'll see you online.